The very important step, basic step is add the slack variables S1 and S2 for the constraints to convert these inequalities into equalities. And the values of x0 here found to be, for the first equation it is 180, for the second equation it is 80. So this is 180 and 80. After substituting these values of x1 and x2 in the objective function, max z is equal to, we are going to get it as 200. Hence, hello dear students, welcome to this session of OR class. I am Mr. Niranjan, Faculty, Department of Computer Science, Vidhyaashram First Grade College, the Temple of Excellence. In my previous class, we have discussed regarding the solution of a linear programming problem using graphical method. Now in this session, I am going to discuss very important concept that is called as solution of a linear programming problem using simplex method. So I am going to discuss today regarding the very important concept that is called a simplex method. Now here let us come to a problem. What is the problem given? Solve the following LPP using simplex method. Now what is the objective function? Max z. So it should be a maximum type problem. The given problem here is maximum type. So we can apply the simplex method easily. Max z is equal to minus 5x1 plus 5x2 subjected to the constraints 2x1 plus 3x2 less than or equal to 180, x1 and plus x2 is less than or equal to 40, and where x1 comma x2 is greater than or equal to 0. Now the problem is of less than equal to type. Now here, to convert these constraints inequalities into equalities, let us add two slack variables S1 and S2. The very important step, basic step is add the slack variables S1 and S2 for the constraints to convert these inequalities into equalities. Now let us consider the two slack variables S1 and S2. S1 and S2 are the slack variables. Here the initial cost of S1 and S2 is 0. Now therefore the standard form of the equation can be written as, the standard form is max z is equal to minus 5x1 plus 5x2 plus 0 s1 plus 0 s2 subjected to the constraints. What are these? 2x1 plus 3x2. Just add one slack variable s1 is equal to 180, and the second equation is x1 plus x2, add another slack variable s2 is equal to 40, and all the non-negative restrictions x1 comma x2 comma s1 and s2 are all greater than or equal to 0. This is the standard form. Now just add the two slack variables s1 and s2. So 2x1 plus 3x2 plus s1 is equal to 180, and s1 plus x2, x1 plus x2 plus s2 is equal to 40. Before going to the initial simplex table, let us write the identity vectors. The identity vectors, let me write down the coefficients of x1, x2, s1 and s2. So what are the coefficients of x1? 2, 3, s1 is 1, s2 is 0. Here the coefficient of x1 is 1, x2 is also 1. And the coefficient of S1 is 0 and 1. So you can observe carefully, this is an identity matrix of order 2 rows and 2 columns. So here the identity matrix forms for the S1 and S2. By finding the initial vectors, here 1 0 0 1 for S1 and S2, I will go for the initial simplex table. The first initial simplex table. In the first initial simplex table, write down the coefficients of x1, x2, s1, s2 and x0 on the first row. In the first row, and in the first and second row, write down the coefficients of x1, x2, s1, s2 and x0. Now the first initial simplex table will be like this. Initial simplex table, the initial vectors are s1 and s2. See here, s1 and s2 are the initial vectors. The values of S1 and S2, basically S1 is 0 and the coefficient of S2 is also 0. The initial cost of S1 and S2 are 0 and 0. Write down the coefficients of x1, x2, s1, s2 from the standard equation. That is, from here the coefficient of x1 is minus 5, x2 is plus 5, s1 is 0 and s2 is equal to 0, minus 5, 5, 0 and 0, the ratio. So this is the initial simplex table. This is initial vector, coefficient of basic variables Cj, x0, x1, x2, s1, s2 and the ratios. Here the initial vectors are s1 and s2. The values, initially the cost of s1 and s2 are 0 and 0. This is zj, and delta j is nothing but zj minus cj. Now write down the coefficients of this x1, x2, s1, s2 from the constraints. What we have? So these are the coefficients, that is 2, 3, 1, 0 and again 1, 1, 0, 1. So I will straight away write this 2, 3, 1, 0. This is 2, 3, 1, 0. And for the second equation 1, 1, 0, 1, 1, 1, 0, 1. And what are the ratios? The ratios are 180 and 40. Here it is 180 and 40. Now find out the value of zj. Zj, usually the zj value will always be is found to be 0. Just multiply this. Multiply with this and add this. 0 into 180 plus 0 into 40. This is 0. For this again 0 into 2. See here 0 into 2. 0 into 2 plus 0 into 1. So you will get it as 0. The value of this is 0. Again 0 into 3 plus 0 into 1 is 0. Again 0 into 1 is 0 plus 0 into 0 is 0. Again 0 into 0 is 0 plus 0 into 1 is equal to 0. Usually the zj column in the initial simplex table will be always zeros. Now find out this delta j. Delta j is equal to zj minus cj. Find out delta j. Now 0 minus 0, yes, 0 minus of minus for x1, this is 0, 0 minus of minus 5, that's equal to 0 plus 5 is equal to 5. This is 5 you will get. Again 0 minus 5, 0 minus 5 is equal to minus 5 here. Again 0 minus 0 is 0 and 0 minus 0 is 0. So this is how we are going to construct the first initial simplex table. Now listen to me. So here write down the coefficients of x1, x2, s1, s2 from the constraints. From first equation we will have 2, 3, 1, 0 and the ratio and the value of x0 is 180. And for the second equation the coefficients of x1 is 1, x2 is 1, s1 is 0 and s2 is equal to 1 and the value is 40. Now find out the value of zj, and zj minus cj will give the value of delta j. Let us identify the least negative in delta j row. In the last row, just identify the least negative value. Here least negative is minus 5. Therefore, this is called the incoming row, incoming variable. These are called incoming variable. So incoming variables. This is called incoming variable. That is, identify the least negative in the last row, that is in delta j row, and represent this as incoming variable. So therefore these are called incoming variables. These are called incoming variables. Now after finding the incoming variables, find out the ratios. The ratios here, the ratios are, since x2 is the incoming variable, so to find the ratio we are going to use this formula. The ratio is equal to x0 divided by this incoming variable x2. So that is x0 divided by x2. Here x0 is 180 divided by 3. 180 by 3 is equal to 60 here. Again 40 divided by 1. 40 by 1 is equal to 40. These are the ratios. So the ratios are 60 and 40. Now just identify the least positive ratio, least positive value in the ratio column. So here in the ratio, least positive value here is 40. So this is the least positive value. So therefore these are called the outgoing variables. This is called an outgoing variable. These are called incoming variables. So here that means the incoming variables are x2 and the outgoing variables are s2. Okay. Now listen to me here. This is the initial simplex table. Just find out the value of delta j is equal to zj minus cj. Identify the least negative value in the last row, and this is called the identify. After identifying, mark this as the incoming variable. Then find out the ratio. The ratio is calculated using the formula x naught divided by this incoming values, x naught divided by x2, 180 by 3 and 40 by 1, 60 and 40. Just identify the least positive value in the ratio column. So in the ratio row, in this column, the least value is 40. Now therefore the outgoing variable, so this is the outgoing variable. That means here incoming variable is x2 and the outgoing variable is s2. Now suppose if all the values in this delta j is equal to zj minus cj are positive, then the optimality is reached. Since it contains negative, so the optimality is not reached, hence we have to go for one more iteration, that is called first iteration. So in the next iteration, this s2 is replaced by the incoming variable x2. So s2 is replaced by x2 and s1 remains the same. And here, since the intersection of these two is 1, this is already 1. If it is not 1, make it as 1 by dividing throughout by that key element. Here the key element is 1, this is the key element. So if it is not 1, divide by that particular key element. But since for this problem the key element is 1, so straight away I will go to the next simplex table, that is the first iteration table. So in the first iteration table, initial vector, so s1 is same, whereas this s2 is replaced by x2 because s2 is the outgoing variable and x2 is the incoming variable, and the coefficient of x2 is 5. So I will write the coefficient of x2 is 5 and s1 is 0, and the remaining values x0, x1, x2, s1, s2 are same. Coefficient of x1 is minus 5, x2 is 5, s1 is 0 and s2 is 0. Now let us come to the previous table. Since here the key element is 1, so there is no need to change. As such, I can enter all these three values, all the values. So here it is 41101, 41101. So see here 41101, because the key element is 1, there is no need to change. Suppose if it is other than 1, just make it as 1 by dividing the entire row with that key element. Now next, convert this 3 as 0. Now to convert this 3 as 0, we are going to use an elementary row operation. Using elementary row operation, convert this 3 as a 0. Now for that, now using elementary operation, r1 dash, so this r1 dash is equal to r1 minus 3 times r2. So what is r1? r1 contains, these are the values 180, 2, 3, 1, 0. This is r1. Multiply with 3 for r2. So if this is r2, if I multiply this with 3, this is 120, again 1 3s are 3, again 1 3s are 3, again 0 and 3. Subtract this, that's it. If you subtract, what you will get? 180 minus 120 is 60, 2 minus 3 is minus 1, 3 minus 3 is 0, 1 minus 0 is 1, 0 minus 3 is minus 3. So these are the values you are going to write. So I will put here 60 minus 1, this is 0 and 1 and minus 3. That's it. See, the elementary row operation is using r1 dash is equal to r1 minus 3 r2. r1 is nothing but the elements in the previous row, that is 180, 2, 3, 1, 0, that is 180, 2, 3, 1, 0, and elements of r2 is nothing but these elements, new elements, that is 40, 1, 1, 0 and 1. Multiply with 3. If you multiply with 3 for this, 40 into 3 is 120, 3 into 1 is 3, 1 into 3 is 3, again 3 into 0 is 0, 3 into 1 is 3. Subtract this, 180 minus 120 is 60, 2 minus 3 is minus 1, 3 minus 3 is 0, 1 minus 0 is 1 and 0 minus 3 is minus 3. Okay. So these are the values. Now let us find out the values of delta j. Similarly, similar procedure to find the delta value. So this is multiplied 0 into 60 is 0, 5 into 4 200, again 0 into minus 1 is 0, 5 into 1 is 5, again 0 into 0, 5 into 1 it is 5, again 0 into 1 is 0, 5 into 0 it is 0, again 0 into 3 is 0, 5 into 1 is 5. These are the values of delta j. Just multiply this. 0 into 60 plus 5 into 40, 200. 0 into minus 1 is 0, plus 5 into 1 is 5. 0 into 0, 0, plus 5 into 1 is 5. 0 plus 5 is 5. 0 into 1 is 0. 5 into 0 it is 0. Again 0 into minus 3 is 0, plus 5 into 1 is 5. So these are the values. Now just find out delta j. What is delta j? So delta j is equal to zj minus cj. So this is as it is. Subtract this. 5 minus of minus 5. This is 5 plus 5 is equal to 10. This is 10. Again 5 minus 5. 5 minus 5, this is 0. 0 minus 0 is 0. Again 5 minus 0. 5 minus 0 is equal to 5. Okay. These are the values of delta j. Now see here, since all the values in this delta j are found to be positive, greater than or equal to 0. So since delta j zj minus cj is greater than or equal to 0, all the values are positive, hence the optimality is reached. Optimality is reached. Here the optimality is reached. Now find out the solution. Here, since the value of x2, this is the solution. Here the value of x2 is equal to 40, whereas x1 is not here. So therefore the values of x1 is not here. X1 is 0, the coefficient of x1 is 0, and x2 is equal to 40. So therefore the value of x1 and x2 are 0 and 40. Now substitute these values in the objective function. So what is the objective function? The objective function is max z is equal to, maximum z is equal to minus 5x1 plus 5x2. So here minus 5 into, what are the values of x1? So x1 and x2. x1 is equal to 0, x2 is equal to 40. Substitute here, x1 is 0 plus 5 into x2 is 40. This is 0 plus 200 is equal to 200. So therefore max z is equal to 200 at x1 is equal to 0 and x2 is equal to 40. So this is how we are going to use to solve a LPP using simplex method. Just find out the initial simplex table and identify whether all the elements here are found to be positive. If it is positive, the optimality is reached. If it is not positive, identify the least negative and consider that as incoming variable. Find out the ratios and identify the least positive in the ratio column and consider that as the outgoing and find out the key element. Here key element is 1. If it is 1, you can proceed with the same values. If it is other than 1, divide with that particular key element and make it as 1 and go for the second table, that is the first iteration. In the first iteration, so it will be 1 and the element above this will be 0. Make this 3 as 0. For this we are going to use the elementary row operation. R1 dash is equal to R1 minus 3R2. Write down R1 and for R2 multiply with 3, subtract. You are going to get these values, that is 60 minus 1, 0, 1 minus 3. See here, it is 1 and above this is 0. Above the key element it is 0. So and find out zj minus cj. If all the values in this delta j are positive, then the optimality is reached. Here all the values are positive or 0, greater than or equal to 0, hence the optimality is reached. Hence the solution is, here the value of x2 is 40. Since x1 is not present, it is absent, therefore x1 is equal to 0. x1 is 0 and x2 is equal to 40. Hence, this is the maximum value we are going to get here. So, therefore, that we will, after substituting these values of x1 and x2 in the objective function, max z is equal to, we are going to get it as 200. Hence, the maximum value is 200 at x1 is 0 and x2 is equal to 40. That's it. This is how we are going to use the simplex method to solve a linear programming problem of a maximization type. Okay. Hope you followed this. That's all regarding today's session. Let us meet with a different problem in the next class. Thank you. Thank you very much.